We're going to do an integration problem with partial fractions. The one we have here is the integral from 1 to square root of 3. And the fraction is numerator 3x squared plus x plus 4. Denominator x cubed plus x. And we're going to integrate that all in terms of x. Our first step would be to break down this denominator as much as we can. So everything will stay the same. It'll still be from 1 to square root of 3. We'll leave the numerator alone. 3x squared plus x plus 4. But the x cubed plus x on the bottom, the denominator, we want to break that down. And it looks like all we can really do is pull an x out. So it'll be x times x squared plus 1. If we could factor that some more, we'd want to. But x squared plus 1 is a sum of squares, so we can't factor anymore. So let's focus on the partial fraction part first of all, and then we can worry about the integration part later. So we have our fraction, one big fraction, and we need to set up the partial fraction. So I'm going to write my big fraction, and I'm going to leave a space, and equals, so the partial fraction, there's two factors down here, two distinct factors. One of them is x, so I'm going to put x on the bottom. It's degree 1, so I don't need a degree on top, so I'll just have a constant. So my first partial fraction will be a over x. I'm going to leave a space for what I'm doing. Plus my other denominator, which is x squared plus 1, and that's degree 2, so I need a degree 1 polynomial on top, so I'll have a bx plus c. So that's the setup from our partial fraction, but then I want to know what the actual value will be for a, b, and c. So when we solve rational equations, we look at our denominator and we try and cancel them all out. So I'm going to multiply everything by x times x squared plus 1. Okay, so three fractions, one on the left, one on the two on the right. So I'm going to multiply through there. So my first fraction or my only fraction on the left, my entire denominator cancels out and leaves me with just the 3x squared plus x plus 4. And then over on the right hand side, the first fraction, I'm going to lose the x, which will leave me with a times x squared plus 1. We'll distribute that in a moment. And the last fraction, I'm going to lose or reduce out the x squared plus 1, which will leave me with bx plus c times x. So let's clean this up, and then we can actually try and solve our a, b, and c. So 3x squared plus x plus 4 equals ax squared plus a plus bx squared plus cx. Okay, so here, let's see what we can do. Let's compare terms. So if I take the x squared terms on the left and right, so for the x squareds, on the left I have 3 of those, and on the right I have a plus b of them. So yeah, let's just use this. So we can compare these. So that gives us one equation. I could write the x squareds in there, but they will cancel out. And then for the x terms, let's see what I have. I have 1x on the left, and then on the right I have c of them. So capturing that was very nice because I know c equals 1 now. Let's go back and highlight the other pink one just so people can see where it came from. And the last thing we have is the constant. So there's a 4 on the left and there's only an a on the right. So even though we had 3 unknowns, very quickly we have already solved 2 of them. So we know c is 1, a is 4, and if I take the fact that a is 4 back up to my 3 equals a plus b, 3 equals a plus b, that's 3 equals 4 plus b, then I'll have b equals -1. So I have my three coefficients. So let's come down here and write our partial fractions out with our limits of integration, because remember we were supposed to be integrating from 1 to square root of 3. I don't know how nice that number is, but let's see. So now we're at the point where we can say that our original fraction can be broken down to a over x. So that is 4 over x plus bx plus c, that's negative 1x plus 1 over x squared plus 1. So that's kind of an interesting thing. And I don't know that we've done one like this, so let's give it a second. Okay, we're integrating two separate fractions, but the second fraction really doesn't have what we want. So I'm going to break it into three completely different parts, and I want you to be able to watch this. Part of this we can go ahead and do, and part of it we can't until we break it apart. So let's see here. Let's do one for the 4 over x. Let's do a second one. Let's make it a little bit neater. But this negative x plus 1 is all over x squared plus 1. I'm going to break that into two completely separate fractions, okay? Because this x can be over the denominator and the 1 can be over the denominator. If you think about how you add fractions together, we could separate them this way as well. So I have one fraction where I'm integrating negative x over x squared plus 1, and then the last one I will have will be the 1 over x squared plus 1. And the reason I broke these apart is because a u substitution just doesn't work on the way this thing looks right now, and it's not a natural log integration itself. But each one of these can be integrated in its own little way. So assuming everything's going right, the first integration, the 4 over x, that will be 4 times the natural log of x. The next one here, where we have negative x over x squared plus 1, we can use a u substitution. We can let u equal x squared plus 1. The du equals 2x dx, so 1/2 du equals x dx. So I thought I would be able to finish this out in one swipe, but we'll have plus. Okay, we're going to replace the x dx with 1/2 du, so that'll be negative 1/2 du, and then there'll be a 1 over u from that u substitution. So that gives me negative 1/2 natural log of u. So in the end, that part becomes, well, not plus, but minus 1/2 natural log of x squared plus 1. Okay, and let me just go ahead and bring down my 4 times natural log of x, if it helps. And let's make those bars a different color, just to make them stand out and not think they're numbered. The last part we have over here is x squared plus 1. I believe that is a inverse tangent. Let me see. It's a trig substitution, but we shouldn't have to do a trig substitution because it's a pretty simple one. Yes, it is trig substitution identity, but what it gives us is plus 1 over a. So the a is 1 anyway, so it'd be tangent inverse of x over a, so just tangent inverse of x. And this is going to be from 1 to square root of 3. So we've got the integration done. Now we just got to plug in. Long problem, but that's what we're doing. We're doing things that we weren't able to do before. So let's let x equals square root of 3. So that would be 4 times the natural log of square root of 3 minus 1/2 natural log of square root of 3 squared plus 1, so that would be 4. these are not crazy. And then plus the tangent inverse of square root of 3. And then we're going to subtract off let x equal 1. So we'll have 4 times the natural log of 1. Anybody remember what natural log of 1 is? It is 0. So let's just go ahead and knock it out. Then we have minus 1/2 natural log of, it looks like it'll be 2. And then we will have plus the tangent inverse of 1. And remember, that's a value, not an angle. So lots to figure out here. Some things that can be cleaned up pretty easily. This 4 times natural log of square root of 3, that 4 can go in as an exponent. You can do this on a calculator, but it will give you the natural log of 9, and then we will have minus, and we can move that 1/2 into the natural log of 4, and that will give us the square root of 4, which is the natural log of 2. And then we need a tangent inverse of square root of 3. So basically that would look like square root of 3 over 2, 1 over 2. This is y, this is x. So that would be, and you can use your calculator for this, but that would give you pi over 3. So we will have plus pi over 3. And then we're going to have over here minus. We've already zapped this out. And then we're going to have minus minus, so that'll be a plus on this one. And once again, we will move the 1/2 in here into the natural log of 2. So we'll have natural log of square root of 2, it looks like. And then tangent inverse of 1. Okay, so that's where the x and the y coordinate are the same, and that happens at pi over 4. Let me write them under what we've got here. So we'll have minus 0 plus natural log of square root of 2, and then we will have minus pi over 4. So there's some things that we can clean up here. I don't know how interested we are, and we are running out of time. But there are things here. We got these 3 natural logs. We have properties of logs that would let us combine that into natural log of 9 square roots of 2 over 2, if we've done that right, because the 2 positive logs would be in the numerator and the negative log would be in the denominator. And then pi over 3 minus pi over 4, I believe that is pi over 12 if we do a common denominator. So let me grab a calculator really quick. This is an even problem, so if you find a mistake, there'll be a lot of work to redo, but it might be worth finding the mistake. As far as an approximation, I'm getting 2.1125. So we got an exact answer, which was no fun. Maybe you went to a decimal much earlier on. But as far as a decimal approximation, here's what we've got. Thank you.